Operation of transformer when the core is non-linear and there are harmonics in supply voltage. Our core is completely non-linear core as the BH curve is not linear, and we are assuming that our supply is completely sinusoidal and we are expecting sinusoidal output voltage. Magnetizing current, it is a peaky wave. This is the magnetizing current waveform, and if there are any third harmonics within the supply, then the output voltage is not completely sinusoidal, whereas tapered output. This is a tapered output. And if there are no third harmonics, then the output waveform can be completely sinusoidal. So mainly, if there are any third harmonics in the supply, those has to be suppressed. So if we consider delta connections on the primary, then the third harmonics will be completely die out as there is closed path for this third harmonics. In case of star connection, then there is no closed path for this third harmonics. So mainly we go for delta connections on the primary side. If we take the basics of harmonics, these are zero sequence, negative sequence, and positive sequence. Zero sequence means cophasors R, Y, and B all are cophasor 3M, where M is odd 1, 3, 5, and so on. Then it will give result 3, 9, 15, and so on. So these are multiples of 3. That means these are triplets. These are the third harmonics. When the sequence is negative sequence, that is 3M minus 1. Minus 1 is representing negative sequence. Plus 1 is representing positive sequence. So here we have to take M as even. For positive sequence and negative sequence, we have to take M as odd in case of zero sequence. So the sequence is zero sequence, negative sequence, positive sequence, zero sequence, negative sequence, and positive sequence, and this cycle repeats. So if we consider delta connections, all the third harmonics will die out, only positive sequence and negative sequence will left. So our mainly goal is we have to kill the third harmonics. By killing the third harmonics, we can have pure sinusoidal waveform on the secondary. Switching transient and doubling effect and inrush current. If the transformer is switched on at zero crossing, then doubling effect will appear. Doubling effect means the flux will be 2 times of its main field flux. So when the transformer is switched on at zero crossing, the flux will go to 2 times of its total flux, which will cause the severe transients. So this will lead to very high magnetizing current. Magnetizing current of 50 times. It draws from the source. This is the inrush current. When we switch on the transformer, then the transformer draws very high currents from the sources. This is because of the doubling effect. That means the transformer is switched on exactly at zero crossing. So because of this doubling effect, the flux is 2 times and the back EMF will be 2 times. It will cause impulse voltages, affect the dielectric strength of the insulation. Total primary winding from top side 40%, from bottom side 40%. Extra insulation has to be provided. Similarly, on the secondary, we have to provide only 5% of winding from the top, only 5% of winding from the bottom. For this portion of winding, we have to provide extra insulation. So this is because to save the transformer windings and their insulations from this inrush currents. So the inrush currents, it mainly appears in HV winding only. It will cause very high repulsive forces, so that we have to brace the windings and insulations very tightly in order to avoid dislocation of these windings and insulations. So that during inrush currents, there will be very high transients. So these transients will also be having DC offset values. Because of this DC offset value, the waveform is completely unsymmetry. So as the waveform is unsymmetry, both even and odd harmonics will present. 2, 3, 4, so on. So these are all harmonics. The most dominant harmonic in transformer will be 2. This is very, very important. Most dominant harmonic in case of transformer is 2. That is even harmonic, not odd harmonic. If waveform is symmetry, then there will be only odd harmonics. Operation of transformer. If the source is other than sinusoidal. So this is the transformer, and we are assuming that our source is not a sinusoidal. It can be impulse, step, ramp, and parabola. In this case, we have two basic formulas: V equals to L di by dt, I equals to 1 by L integration of V of t dt. These are the two formulas with reference to inductor, because on large scale, our transformer is almost equal to inductor. We have to consider impulse, step, ramp, and parabola of either voltage or either current. If current is known, we have to get voltage, then current is differentiated. If the voltage is known, then if we have to get the current, then voltage has to be integrated. So in this case, if you go RHS side, that is integration. If you go LHS side, that is differentiation. For example, if the current is square waveform, then the voltage will be differentiation of square. Differentiation of square will be impulse. So this is voltage. If the current waveform is ramp, differentiation of ramp is step. So the voltage will be step. In this case, if the voltage waveform is ramp, what is the current? If the voltage waveform is ramp, then the current is integration of voltage. Integration of voltage will be parabola. So this. So in this way, we can simply find the type of waveform. If one is known, the other type of waveform we can find.